Today we are going to study about density of state in a one-dimensional material. First of all, let's understand what is a one-dimensional material. One-dimensional material is a material in which charge carriers are confined in two directions and they are free to move in one direction. In this case, like we have taken x, y, and x and y axis to be the dimension is very small, while in the z axis the size of the material is very large. Now, when we say small, it means that Lx and Ly is of the order of de Broglie wavelength of the charge carriers that we are talking about. So in this case, if we are talking about electrons, then the de Broglie wavelength of the electron must be less than the dimension of the structure in x and y direction. The energy spectrum for such a structure is given by um, this relation, where because we know that in x and y direction the motion of the charge carrier will be quantized, while in the z direction the motion will be continuous. Therefore, because of this quantization, the k values will have discrete values, while in the z direction k will have a continuous distribution. So this energy spectrum is actually will give you, it is a one-dimensional parabolic dispersion relation, because it will give you a parabola in the z direction, while in x and y direction it is quantized. So if we now compare it with the bulk, you see that in bulk all the k values were allowed, and it was a parabola in all the three directions. In the two-dimensional material, the dispersion relation is parabola in two directions, while in one direction it is quantized. While in and also if we have to draw a equal energy surface in for a 3D material, it will be a sphere, while in a 2D material it will be a circle. While in a one-dimensional material, you see for each value of k you will have a line of energy, and energy will be constant on in one dimension. So also because it is a parabola in one direction, so in order to find the minimum value of the energy of the subband, the minimum energy will be when kz will be equal to 0. So the first minima will be 1 1 e1 1, so you can put the value of nx and ny as 1 1 and find the value of energy, where we have neglected ec, which is okay. And for the second subband it will be first can be 1 and 2, and they can be reciprocated also. Nx can be 2 and ny can be 1, because they both will have the same energy, and so on. So you'll get these all subbands. Here, just for clarity, I have just shown two subbands, but it will be n number of subbands. So in the K diagram, you see that in a three-dimensional material, you will have all the values will be permitted in x, y, and z direction, because the motion is continuous in all the three directions. While in two-dimensional material, it is continuous in y, continuous in z direction, while it will be discrete in the x direction. So not all values of x will be allowed. So the equal energy will be at a surface which will be perpendicular to the kx direction, and the radius will be kx square plus kz square in this direction, in this particular case. While for one-dimensional material, it will just, the energy will be continuous in only one line, while k vector will be discrete in kx and ky direction. So it means that in the k space, we are just taking an infinitesimally thick material, where you'll just have a line of k points in the z direction, while because half of the points will be in the negative axis and half of it will be in the positive axis. So if we have to find the total number of states, what we can do is we can have the length of the entire K space with the maximum kz value corresponding to the maximum energy permissible. So the total length will be in this case will be kz, and the length of one state will be pi upon Lz. So total length divided by length of one state, but we'll have to multiply it with half because there are negative values of k also, which don't make any sense. While we will have to multiply it with 2 because the number of states should be doubled to take care of the 2 spin states of the electron, and so this will be the number of energy states that will be permitted. So now we can replace kz from the dispersion relation of the material. So from here you can find out that a k depends on E in such a manner. So you can replace it here, and you see that n actually depends upon under root of E minus E nx ny because Ec is a constant. So if we have to find out the density of states now, it will be 1 upon length in the real space, and derivative of the number of states with respect to energy. So it will give you density of states, which will depend inversely on E minus E nx ny. Ec you can neglect. In some of the books they have neglected Ec because it is just a constant number, so it will not matter actually. So what this density of states means is that whenever E will be equal to Ec plus E nx ny, density of state will shoot up. It will go to infinity. Okay, and then as E increases more than Ec plus E nx ny, then it will decrease as under root of E. So first it will shoot and then it will decrease, and the function will be under root of E. So it will decrease as under root of E. So if we draw this function, it will look something like this. So I've drawn for a 3-dimensional material, 2-dimensional material and a 1-dimensional material. You see that there will be no energy states below E11. So it will be 0 from here to here. While as the energy will reach the minimum of the subband, it will shoot to infinity. And then it will decrease as 1 upon under root of E minus En. While again at 1, 2, it will shoot to infinity and then it will decrease as a root of E minus En. So you see that first of all that this Ec here is at a lower energy, E1 is at higher energy, and E11 is yet at higher energy. So if I had to draw a valence band also in the other side, it will give you the band gap, and so band gap will increase as you go from a 2-dimensional material to a 1-dimensional material. So let's try to understand this, and then maybe I'll discuss that case also. So this is how the density of states will look like. Now what does it mean that it shoots up and then it is a delta, almost like a delta function here, and then it decreases? So if we have a look at the subbands, you see that at this lowest value of the subband, the density will be very high and very sharp. So a high density of states will be here, and as you move above, the density of states will decrease, and so on for the next subband also. And in the general case, you can put you can multiply it with some Heaviside function, and so that the replication of the function can take place at each value of energy. So this Heaviside function is such that it will have, if it is less than that particular energy, it will be 0, and if it is greater than that particular energy, it will be 1. So it will be change between 0 and 1, giving you a kind of a function which first has some value and then it decreases. Okay. So here actually I was talking about, if we have to draw it for the valence band also, then it would look something like this. So let us say that this is for the 3-dimensional material, this is for a 2-dimensional material, and this is for a one-dimensional material. So let us say that this is the valence band. So if this is the band gap for a bulk material, then this will be the band gap for a two-dimensional material, while this will be the band gap for three-dimensional material.